Flow. What do we mean by flow? Just what's flow? What's flow? What do we mean by flow sensors? I'm sorry.
Direction? No.
Flow is basically the rate or the speed a fluid is in motion, right? Of course, we already know this one. So we've gone over position, we've gone over weight, we've gone over pressure, we're going to do flow, we went temperature, light, we've done liquid levels, we've done motion, we've done proximity, and we haven't done viscosity. What's viscosity? The thickness of a liquid, right? So units of flow. So what we're going to do is it's going to be a volume at a rate, right? You understand that? Standard liters per minute, cubic meters per second. U.S. customary, which we use over here, is gallons per minute or cubic feet per second. Everybody okay? So y'all got any flow meters at Brother? And I guess it's in what, liters per minute?
Remember the
Cubic
hair
feet.
dryers.
What's that?
That is a hand hair
Really?
dryer.
Yeah, sure.
Really big burger.
So this is the same thing, guys. We got to take some type of mechanical sensor. And in flow, you got to get in, the sensor itself has to get into the flow of the fluid, right? Most everybody's done that where you're kind of like a flow sensor. You're driving along in the car, you got the window down. What's the tendency you want to do? Stick your hand out the window and let it do what?
Fly.
Yeah, fly. So if you knew how much force you put against your arm, then you could calibrate the flow, how fast the wind was going past the car, right? So we have to have some type of sensor which creates a displacement, then we have a transducer that's going to take that and give us an electrical signal, and then we might have signal conditioning, and this would be where you're a threshold, where you have a digital sensor where you set a threshold. It's just like force sensors. The sensing element itself is analog, right? You understand? Because it displays a certain thing. And so and then my transducer is probably going to change that and change it into an analog signal that changes between 0 and some voltage. And then what we do is we'll have a threshold sensor, which basically we can come in and set a threshold. And then sometimes it's actually adjustable. Sometimes you can actually adjust where it does what? Where it actually trips. And a good example is this pressure sensor. So I can change when output 1 and output 2 goes. If I'm going to go digital, this is going to be a threshold detector, right? If we're going to take the analog output, then we would take it off here. So this pressure sensor that we have gives us both these options. We can get an analog output that actually gives us a representation, a voltage representation of the pressure, or we can have digital outputs which tells us when we exceed a certain pressure, right? That makes sense? Or drop below that. Typical gauges, we got all kinds of gauges. More and more you're going to move away from these actual dial indicators, and we're moving to some type of digital outputs on just about everything now. All right. Difference in pressure based on the orifice of flow sensors. We have one that measures the differential pressure. We have rotometers, spring pistons, turbines, paddle wheels, vanes, magnetic flow meters, and ultrasonic flow meters we'll look at in this presentation. Is there more? Probably, but this covers a wide range. This is called a piston and spring. So basically we have a piston and it's working against a calibrated spring. You know, the springs, uh, even a standard spring would compress or expand at a precise force. A calibrated spring means these guys have trimmed so they expand and contract at a precise force that we understand, right? You understand? So what we have is we have a piston up here. This guy comes up here and strikes that piston. It generates a force, which does what? Works against a calibrated spring, and then we use that to measure how fast it's moving to generate that force to give us a flow. This makes sense? Pretty simple. This is used a lot. This is called an orifice plate. And what we do is we have some type of thing that measures a pressure differential. And then what we do is we take a flow, we force it through an orifice. This causes it to speed up, which generates a low pressure. Then it comes up here, it's at a slightly different pressure, and the pressure differential would give us the flow rate. Very simple sensor. The problem is that this guy here does impede the flow a little bit, so we're going to lose pressure. I'm sorry, it's not going to impede the flow, but it will lose pressure on. So the output pressure would be a little less input. So one of the guys in the thing that was talking about said that a flow control valve doesn't change pressure; it changes rate, and that's not true. Because you can't meter the flow without changing pressure a little bit, right? In fact, one of the labs that we do in fluid power is we put a pressure valve across the flow control valve. And when we put it down, you'll see it give a little pulse. Now, when the flow stops, the pressure is the same, right? You understand? So it's just like resistors. If you have no current flow through a resistor, you don't get a voltage drop. But so when you have a flow through a flow control valve, there is a pressure differential between the input and the output. But as soon as it pushes against something and slows down, the flow rate would go down. And of course, when it finally hits the end, then the pressure, we would get no pressure loss because there's no more flow. This is a Ventura. This is a lot better. This guy doesn't impede the flow as much as a orifice plate does. So all we do is we take a flow, we force it through a Ventura, and we run into this a lot. We use these guys to actually create a vacuum. So what we do is we have one pressure on this side. This guy has the speed up to go through the Ventura. Right, you understand, which causes a low pressure right here, a lower pressure right there, and the difference between the one before the Ventura and at the Ventura would give us the actual, the difference in pressure would give us the flow. And yeah, it could be. We use these guys to generate a vacuum, and that's a perfect example. We literally use these guys to generate a vacuum. So if we were over on the two manufacturing lines over there, each one of them uses a vacuum, but it don't have a vacuum pump. And so how does it generate a vacuum? It does exactly the same thing that we're talking about here. So that's a really good point. But how much vacuum it generates is depending on what? The rate of the flow. So normally these guys will have a flow control valve on them. And you can literally change, you can either literally change the vacuum by changing the flow. This is a PDOT tube. Go ahead.
More flow, higher vacuum.
Yeah, more flow, the higher vacuum. These are PDOT tubes. PDOT. These I've got a lot of experience with. These were one of the speed indicators that we use on airplanes. So if you ever get close to the nose of an airplane, you see these two L-shaped tubes coming out pointing toward the flow. And basically, what you have to do on PDOT tubes, you have to compare it to something. So what we do is we have one we call the static pressure. So this would be static right here. and then we have one that's the dynamic pressure. And then what they do is they compare the two. So if you ever looked at an airplane, if you started walking down the sides, you'd see little holes on the side of the airplane. And that would be where you do the static at. And then on the front of the plane, you'd see these two PDOT tubes sticking out. Our PDOT tubes were heated because these things get up. Our plane could fly at 32,000 feet, and some of these planes, and the PDOT tubes would actually freeze up, so they were heated. And sometimes, and they put covers of them when they're parked because dirt daubers like to make their nest in these little holes. Yeah. So. And every once in a while, they'd forget to take the covers off. And of course, that was the flight engineer's part because that was part of the pre-flight. They'd burn the covers up. But so PDOT tubes, y'all understand how these things work? Pretty simple. Like I said, every airplane you're going to see them. But basically, it puts it in the flow. We have to have two of them, right? We have to have a static tube that measures the static pressure. Y'all see which one that is? Oh, there it is. It's labeled. Yeah. Sorry. How did I do that? So this would be the one that's measuring what? The static pressure. And this would be the one that's measuring the actual round pressure. And then they compare them against each other. Because an airplane, as you get, the higher you go, the less flow you get, right? You understand that? Because it's thinner. That's why they would compare it against a static pressure, and they would always get the right airspeed. So they wouldn't if they was using that type of airspeed. Rotometer. This works a lot like a piston type, except this is dealing with gravity. And you see these a lot because they're mounted vertical. I don't know if you've ever seen them, and they're very, very simple. So they basically work off of gravity. So the flow goes through it. The rate of the flow would counteract the gravity. This would be weighted, and how far it rose would be give you a flow. And we got one of these, though, I think. Nope. This is a different type. This is actually oh, there it is. This has got a metal ball. This is what you do when you kind of do your hand out in the car. This is what we call a vane. So basically, we just put a flat plate into the flow. It's got a spring on it, a calibrated spring, and when it flows, what does it do with the vane? It causes the vane to displace, and the amount of displacement, this would be proportional to the flow. Of course, this would be just, so here they're using an actual potentiometer to measure the actual displacement of the vane. And then this would give us a voltage that's proportional to the displacement, which would give us an indication of the flow. This guy here is very simple. This is really used a lot. This should be obvious. This is the paddle wheel. So what we do is bring the flow in on one side, causing the thing to do what? Spin. The faster it spins would be the what? The faster the flow. So this is pretty simple to understand. Are we okay? Pretty straightforward. This works. This is very similar. I've seen these before, where we actually put a turbine inside the flow. The liquid comes in, passes over the turbine. The turbine does what? Spins. Here they have a magnet. The turbine has a magnet on it, and they have a Holotech sensor. So the Holotech sensor would convert it into a pulse, and the rate of the pulses would give us the speed, and the rate of the speed would give us the flow, right? This makes sense? You okay? What?
Am I getting colder? No.
Sort of. It would be. It would be like it'd be kind of like an incremental code. Because what we do is, you're exactly right. We get pulses, and the rate of the pulses would give us a watt. The speed. Then we have a magnetic flow sensor. Here what we do is so what's required to induce an EMF? Let me get my thing up there. Gotta have a what? Number one. Gotta have a magnetic field. Then we gotta have a conductor, right? And then we gotta have motion. So this has got to be some type of fluid that would be able to handle this. So what we do prior to the sensors, we have a magnetic field. So the fluid passes through a magnetic field. And then that fluid passes through these coils right here that's mounted on each side. And the rate of the motion would give us what? Flow, right? This would work with most liquids. Probably wouldn't work with like distilled water, but most liquids have particles in them that would react to the magnetic field. So this would work on most liquids. Probably wouldn't work on gases. When we talk about fluid, what is a fluid? I should have put that definition up there. What is a fluid? I need to do that. What is a fluid? Most people think liquid, and I used to think that myself. I didn't understand what a fluid was. A fluid is anything that has no fixed shape. It takes the shape of whatever it's put into, right? You understand that? So I'm sitting in a fluid right now. Huh?
What about Play-Doh?
Play-Doh is considered, and it moves very easily with what? With a difference of potential. Yeah, so to be that. So gases, so basically fluids are gases and liquids.
So Play-Doh would probably be considered like slurred.
It's what we call a slurry.
Yeah.
Which means it's a fluid that don't move what?
Wow.
Yeah, slime. Let's don't talk about slime. My granddaughter, she's 10, she got into that one time. And we made slime. They don't tell it how many gallons of slime we made. And stretched it out. And see, we could blow it up and make bubbles out of it and make it pop and put different stuffs in it. They don't tell how many gallons of glue we bought. Elmer's glue. So a fluid is anything that does what? Does not have it takes the shape of whatever it's put in, right? And it moves freely with a difference of pressure. So basically, we talk about these would be liquids, and these would be gases.
You said air is a fluid?
Air is a fluid. Air is a fluid. Gases are fluid. And we have two technologies that we use to generate pressure. We have what we call pneumatics, which uses gases as a fluid. And then we have hydraulics, which use liquid as a fluid. And like I said, I'm the one, I thought that for years. That fluids were what? Liquids. Look it up. So this guy would probably be used with liquids, and of course the liquids that we're talking about can't be. It could probably like distilled water, but just about every fluid has something in it, right? You understand that this would react to. Look at this. I don't know. I wish I had a size that would actually give us an indication of the size of these things. Then we'll have what we call ultrasonic. These works on what we call a Doppler effect. So Doppler effect depends on sonic conductivity, particle density, and flow profile, effect by temperature, density, and viscosity. Unstable for high accuracy. So we wouldn't use these guys for extremely high accuracy, but this would give us a round of, it's like in electronics, in electronics, our math is perfect, but our components are not, right? And if we can live with that tolerance, then we're okay. Time of flight, these are pretty accurate. Measures times, bidirectional flow, don't think about temperature, density, or viscosity. These are very accurate. They're accurate between one. And you can tell these guys because these have the Doppler effect is looking for it's looking for a shift it's looking on a shift in the reflection, right? Understand that. And then the time of flight is looking at how fast it goes back and how fast it comes back to you, right? How it goes out and comes back. These, you'll see these will be strapped on to one side of the pipe. These right here, you have to have one-on-one. And they have to be offset by this angle. And you'll see it'll be on both sides of the pipe that it's trying to measure the flow through. I think I got pictures on the next slide. So this would be a Doppler effect. This would be a time of flight. See the indicators? Here they got 3 of them that are summing together. So it's a total of 6 because it's fluid flowing at the same rate throughout the pipe. No, where's it flowing the fastest? In the center. And the slowest up against the walls, right?
So what's the point of all these sensors that do the same? They're measuring the same.
It all depends on, of course, how accurate you want to be. What are you gonna input these into? Right? Whether you're going to use just a regular dial indicator, whether you're going to use a programmable controller, or whether you're going to input these into a computer. What do we need? What is it going to give us out? And what application we're going to do it? And basically, another thing, who's the engineers that design your system? What do they prefer? And you've always got engineers that prefer to do things what? Different ways, yeah. So there's a lot that deals with it. This right here would actually be, so what would this be? Only on one side.
The Doppler.
Doppler, yeah. And then what would this be?
Time flight.
Time of flight.
This is what it's talking.
This one on the top, it looks like it's a Doppler because it don't have a sensor on the bottom. These over here is definitely time of flight. And what this is doing is this looks like the top one is actually averaging out what through the entire pipe. Not only what's flowing in the center, but also on the outside edges. So what do we look at? We looked at a lot. And like I said, and Alex had answered a really good question. What determines which one you're going to use? It's the application. And what are you going to do with the information? If you're going to take the flow rate and input it into a computer or something like that, then you're going to have to get it into a form that the computer understands. Either a series of pulses, which is what the turbine does, or a voltage that means something to our PLCs and stuff like that. So that's a really good question. And then, of course, a lot of it deals with the engineer that's designing your system. What do they prefer? What have they dealt with before? What do they understand? A lot of engineers don't want to learn new things, right? You understand? It's just like us. And if they've dealt with a certain time, they understand it completely, then that's the ones they're going to use when they engineer. So any questions on any of these? So I need to put that in the very front. What is a fluid? Because flow sensors are measuring the rate of flow of a what? Of a fluid. And they're given in volume over time. Right? You understand? So when we talk about these, we have liters per minute. So liters is a what? Is a volume over time. So all your rate of flows is a volume over time. Cubic, which would be an area, right? Cubic centimeters per second. So cubic centimeters are cubic meters, I'm sorry. and I've seen cubic centimeters, by the way. Meters cubed, that would give us a volume, right? You understand, per second. Of course, US customary, which we'll see a lot over here, is going to be in every, we understand this. We've seen this before, you know, on fuel pumps. Your compressors are rated in gallons per minute, which tells you the speed of the rate, right? And then cubic feet per second. This would be this one, but it would be the same thing for the US customary unit. So over here, what you're going to run in and where we're at now would depend on where you go to work at. If you go to work at, so we're getting a lot of companies that are not, they're not headquartered here. We have plants here, but they're not headquartered here. They're from another country. Odds are, if it's from another country, it's probably going to use what? Probably going to use SI units. People that's stationed over here are probably going to use what? Yeah, so if you go to work for any company that makes Chevrolets, they're probably going to use this. But if you go to any work of companies that makes foreign cars, what we still call foreign cars, but technically they're not foreign cars anymore. We call them foreign cars because they're mainly headquartered where? Yeah. Originally, foreign cars was foreign cars. If y'all remember then, they did what? They made them overseas and shipped them over here. Now, a lot of them are made over here instead of being shipped because now it's cheaper for them to do what? Make them here than it is to what? Make them there and ship them. So we call Mercedes a foreign car. They make foreign cars, but that's not exactly true anymore. So this would probably be, you need to know on the test. So why do we measure flow in? It's what? Volume over time. So volume is different than area. So area is what? Length times width. Volume is always length times width times height, right? You understand? But here we're dealing with a cube, which means the height and the length and the width are all the same size. So that's why we can use cubic feet per minute, because we're dealing with what? Cubes. Liters per minute. Standard liters per minute. Why do they use standard? We'd have to look at that why we call it standard liters per minute. But this would be the abbreviations right here. So on the actual indicator itself, this is probably what you'd see, right? Okay. Or you might see something like this. Okay? Okay, guys, you'll take a 10-minute break. We could, or we could go ahead and get vision sensors out of the way.
You don't sensors out of the way. Actually, sensors.